The objective of this lab is to investigate instruments and techniques for measuring length or distance. Length measurement is a fundamental building block of metrology. Instruments and techniques available for length measurement are too numerous to mention. For that reason, we will limit today's lab to discussing length measurement using gauge blocks, vernier calipers, micrometer, capacitance gauge, electronic indicator gauge, and laser interferometer. While greatly differing in principle, accuracy, and repeatability, each of these measurement tools has its own place in the area of length measurement. Before choosing a measurement device, several questions should be answered. What is the required resolution? What degree of accuracy is necessary? What is the range of measurement? Will measurement forces significantly distort the specimen? Will the measurement uncertainty be determined by the measuring instrument, or will the environment be the limiting factor? As we will see, there is no singularly superior instrument, but numerous instruments with varying degrees of appropriateness for specific tasks. The use of gauge blocks, like many measurement procedures, involves the comparison of some unknown dimension to a reference standard. Gauge blocks, sometimes referred to as Joe blocks after their inventor Carl Johansson, are length standards which have been precisely ground and lapped to a prescribed length. To avoid the effects of thermal expansion, the distance between the gauge block's two ground and lapped ends, or terminal surfaces, is measured at Johansson's standard of 20 degrees Celsius or 68 degrees Fahrenheit. Often made of nickel steel or ceramic, gauge blocks are fabricated with attention to terminal surface hardness, microfinish, flatness, and parallelism. These terminal surfaces must be treated with extreme care to avoid scratching and corrosion. After each use, terminal surfaces should be wiped clean with a chamois cloth and lightweight oil. Using a basic set of various length gauge blocks, random lengths can be measured by joining the blocks necessary to form a stack of blocks of the desired dimension. The terminal surfaces of the two gauge blocks are wrung or twisted together and held secure by a ringing film approximately 1/4 of a microinch thick. Since these film thicknesses are measurable, the total number of ringing films present should be minimized to avoid undermining the accuracy of the measurement. Gauge blocks can be used to directly measure internal dimensions or may be used with attachments or intermediary tools to measure external dimensions. Temperature variations can destroy the integrity of length measurements. Since these gauge blocks are fabricated and inspected at the standard 20 degrees Celsius, use at another temperature would result in measurement error given by the temperature difference and the coefficient of thermal expansion of the gauge block material. Therefore, when conducting precise measurements, work in an environment maintained at 20 degrees Celsius, wear gloves, and minimize handling to avoid body heating of the specimen and gauge blocks, and allow time for thermal equilibration of the specimen and gauge blocks. Gravity is another source of potential measurement error. For example, the terminal surfaces of this long, horizontally oriented gauge block are no longer parallel because of gravitational sagging. If the terminal surfaces are not parallel, different length values will be obtained depending on the points referenced. However, if the gauge block supports are located at the airy points, as shown here, the terminal surfaces will be parallel and the length value will be constant regardless of the points referenced. However, because of the deflection of the gauge block, the measured length will be less, although by a very small amount. Gauge blocks are fabricated to different levels of accuracy or tolerance grades. Grade selection of gauge blocks must be wisely made based on required accuracy and budget constraints. The grade of the gauge block set used in today's lab is A+ or 2. This means that measurements made with a 1-inch gauge block have at best 6 microinches of uncertainty. With their high resolution and accuracy, gauge blocks may be used to calibrate other less precise measurement tools such as calipers and micrometers. Vernier calipers consist of a pair of blades. One blade is fixed, the other blade can be moved along a slide. The ground terminal surfaces of the two blades are brought together and the slide scales read 0. Length measurements of a part, that is, the distance of separation between the two terminal surfaces, when contacting the part surfaces are made by reading the displacement of the slide. Calipers are also available where the displacement is read from an analog dial or a digital readout. The typical resolution for calipers is 1/1000th of an inch, or 1 mil. To gauge a sample, hold the sample and calipers as shown. Press in the lock with your thumb and push or pull the slide to bring the blades to the appropriate spacing for the sample to be measured. Gently bring the blades into contact with the sample. Do not use excessive force. Remember that measurement forces should be minimized. Notice that this set of calipers facilitates direct internal and external gauging. Note that there are two scales to be read. The 0 to 7.3 inch scale with the 0.025 inch graduations is located along the length of the fixed portion of the slide. The auxiliary or vernier scale, named after the French mathematician Pierre Vernier, is composed of 0.001 inch graduations and is located along the movable portion of the slide. To make a reading, first identify the lesser of the two 0.025 inch graduations between which the zero line lies. In this example, the zero line lies between the 1.275 inch and the 1.3 inch graduations. This first portion of the measurement represents 1.275 inches. Next, determine which 0.001 inch graduation along the movable slide most closely lines up with any graduation along the fixed slide. Here, the 0.021 inch graduation lines up best with the 1.95 inch graduation representing 0.021 inches. Finally, add the length components from each step, 1.275 inches and 0.021 inches, to obtain the overall length of 1.296 inches. A significant issue in contact measurement is the probing or measurement force. Variation in this force will obviously yield measurement variations. Therefore, the level of force used in the calibration of the calipers should also be used in the actual measurements. Unfortunately, these calipers provide no means of ensuring a uniform measurement force. Instruments of this sort, which rely heavily on the skill of the operator, can often produce uncertain and inaccurate measurements. In addition to the problem of variable measurement force, the caliper's design represents an undesirable situation where the measurement axis does not coincide with the probing axis, thereby creating the potential for significant measurement error. That is, if these non-collinear axes were also slightly non-parallel, an error would result of magnitude equal to the offset distance times the sine of the angle of non-parallelism. In this example, the offset, usually referred to as the Abbe offset after Ernst Abbe, is 1 inch. If we assume 5 minutes of angular misalignment, the resultant measurement error would exceed 1/1000th of an inch. For these calipers, that error would be on the order of the measurement resolution and would thus introduce appreciable error into the measured dimension. From this example, Abbe offsets can be seen as situations to avoid. The design of the micrometer does avoid Abbe offsets as the axis of displacement and the axis of measurement are collinear. Furthermore, this micrometer features a torque handle to facilitate uniform measurement forces. A micrometer consists of a terminal surface fixed to the main micrometer body and another terminal surface attached to the translating but non-rotating shaft. By rotating the micrometer barrel, the shaft is translated via a precise, fine-pitch lead screw. The translation of the shaft is indicated by a primary scale of 0.025 inch graduations along the micrometer body, a secondary scale of 0.001 inch graduations around the micrometer barrel, and a vernier scale of 0.0001 inch graduations around the micrometer body. This resolution of 1/10,000th of an inch is typical for micrometers. To gauge a specimen, hold the specimen and micrometer as shown. Adjust the position of the shaft by rotating the micrometer barrel with thumb and finger. At the point of impending contact, advance the shaft by rotating the torque handle until it slips. Note that the micrometer permits direct external gauging only. Internal measurements require an intermediary standard. The range of measurement for this micrometer is 0 to 1 inch. However, while the 1 inch positioning range is fairly standard, different measurement ranges are available. The micrometer shown here has a measurement range of 1 to 2 inches. To make a micrometer reading, first locate the largest .025-inch graduation visible, that is, not covered by the barrel. In this example, the .275-inch mark is the last one visible. Next, identify the lesser of the two .001-inch graduations between which the indicator line lies. Here that is the .005-inch mark. Now determine which .0001-inch graduation most closely lines up with any .001-inch graduation. In this case, the .0005-inch graduation lines up best with the .013-inch graduation, representing .0005 inches. Adding the length components from each step, .275 inches, .005 inches, and .0005 inches, we obtain the overall length of .2805 inches. Capacitance gauges offer high resolution, stability, linearity, and non-contacting gauging for small displacements. Capacitance gauge operation can be basically modeled as two parallel conducting plates separated by some dielectric material. Typically, the target area acts as the ground plate, the surface of the probe acts as the plate of non-zero potential, and air is often the dielectric material. Variable gap capacitance gauges are based on the principle that measured capacitance changes are inversely proportional to changes in the separation distance. Unfortunately, this relationship is not linear. Therefore, electronic circuitry is necessary to linearize the measurement signal. Differentiating the previous expression reveals that the measured capacitance and the measurement sensitivity increase as the separation distance decreases. This effect is limited by the voltage breakdown limit of the dielectric material. Selecting a dielectric material with a higher dielectric constant, such as oil, will provide improved performance. The capacitance or cap gauge shown here has a resolution of plus or minus 1/2 microinch as determined by the 10 millivolts of static noise. The linearity of the system is 0.4% of the full scale. The frequency response is 40 kilohertz, making the system very attractive for dynamic measurement. The diameter of the active or sensing area of the probe is 0.066 inches. The diameter of the target area should be a minimum of 0.132 inches. The operation of the cap gauge involves an averaging of the capacitance over the sensing areas, thereby increasing measurement repeatability by reducing the effects of transient phenomena. The nominal separation of the probe and target sensing areas is 0.0042 inches. Fixturing for the probe should be rigid, free of vibration, and thermally stable. This cap gauge console offers 3 measurement ranges. Range A has a spread of plus or minus 0.001 inches. Range B has a spread of plus or minus 0.0005 inches. And range C has a spread of plus or minus 0.0001 inches. In addition to static displacements, total indicated reading and positive and negative peak displacement values can be displayed. The cap gauge console allows single probe gauging, 2 probe differential gauging, and 2 probe summing gauging. The analog signal representing the measured displacement is plus or minus 10 volts with a scaling factor of 100 microinches per volt, regardless of the range selection. Auxiliary outputs allow differentiation of the displacement signal to obtain velocity and acceleration values. While cap gauges do offer many benefits, some disadvantages should be noted. For this particular unit, the nominal separation or working distance is 4/1000 of an inch.